All right, I hope you watched that video. To give you a sort of, it's a nice little animation from Purdue University that shows the solvent particles escaping from a pure liquid and then from a solution. So I'm going to draw a picture here as well. Won't be as nice as the animation, but so what I've got is a beaker of pure liquid. And at the surface there, if I think about, there are particles, of course. So I'm going to draw 900 of these. Go get a cup of coffee, come back. And of course, these are escaping. And that gives rise to vapor pressure. A common example of this is if you go to put gas in a car on a hot day and you open up the gas cap, you hear that whoosh coming out of there. That's the vapor pressure of the gasoline escaping. So I've got some vapor pressure from the evaporation. Now over here, let's see, I'll make a note. This is pure solvent, so not a solution. In this beaker, or whatever the heck this poorly drawn flask is, I've got my solvent particles, but interspersed in there are solute particles. So on this side, I've got a solution. And one way to think about it is the solute particles, they simply block or somehow retain the solvent particles from escaping. So I get a much lower. We could think of it as, well, let's say this. We could say, let's say, solute particles block evaporation. And so what we have is a lower vapor pressure. That's really poorly written, but so we've got lower vapor pressure. It makes sense. There's a couple of ways. One is the solute particles are basically just blocking the solvent particles don't have as much access to that surface to escape. Another way to think about it, of course, is the solute particles have some IMF that's sort of retaining the solvent particles from escaping. So kind of a nice, easy to understand mechanism. Now here's where it gets really cool. So, what do you think about this? I'm going to draw a little graphic here, temperature and vapor pressure. And I'm going to make a note right there. That's atmospheric pressure. So this is millimeters of mercury or ATMs or PSI or something. And this is atmospheric pressure. So 1 ATM. Now, we know what happens when we heat up a liquid. There's more and more evaporation. Vapor pressure goes up and up and up. So it goes up, 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 and we saw this in. And at that point, when the pressure of the vapor hits the atmospheric pressure, boom, we get boiling going on. The pressure goes up, up, up. Eventually, it's able to sort of push back against the atmospheric pressure, and we get the boiling point. At that temperature, the pressure is equal to the atmospheric pressure. So this is pure solvent. Now, we already said up here the vapor pressure will be lower. So the same thing happens for the solution, only it's all going to happen at a lower temperature. So it's going to trail along like that. Now, at the normal boiling point, the pressure isn't high enough to start boiling. So this thing continues on like that, which means here is the boiling point of the solution. Pretty cool. So solution, lower vapor pressure. When I look at it in terms of temperature and vapor pressure pushing back against atmospheric pressure, that means the solution has to go to a higher temperature to get the same vapor pressure. So a solution has to go to a higher temperature to boil. So I'll make a note. This is the solution.